Okay, so the next speaker is Professor Moller from the University of Texas at Dallas. And so he published many favorite books, and so one of them is in front of this room, the neuroplasticity and disorders of the nervous system. So today's his talk is about neuroplasticity for good and for bad. Please, Professor Moller.
Mr. Chairman, Professor Morase, ladies and gentlemen, it's a real great pleasure and a great honor to be here. And we have all enjoyed many days already of very interesting and diverse views on physics. I think this is a department of physics, but the topics have been all over, and that has really been exciting and quite new thing. I don't usually go to physics meetings, but I can't imagine that physics meetings usually have that kind of variety of topics. I would like to use the next hour, or 45 minutes actually, for discussing neuroplasticity. The fact that the brain is plastic has been recognized for a long time, but it is only relatively recently that it has come into the attention of medicine, attention of researchers in general. And we all know that the blueprint of the central nervous system is laid by genetics, and epigenetics, also relatively recently recognized factor, and its organization can be changed throughout life. It was earlier believed that neuroplasticity was only active in children, in the young individual, but now it is recognized well that it also applies to adults. It is a kind of a mid-course correction. We have the path staked out by genetics, but it needs to be corrected in many ways. Like any other kind of corrections, that correction sometimes doesn't go right. It can go wrong, and this will cause diseases and disorders. So we can say that neuroplasticity, activation of neuroplasticity, can be both beneficial and harmful. And what we call plasticity disorders may result if it is being harmful going wrong. But it is definitely necessary for the normal development of the central nervous system. Central nervous system comprises both the spinal cord and the brain. And sometimes the spinal cord has been neglected when discussions about neuroplasticity has been made, but it's definitely very important. So neuroplasticity is a property of the central nervous system. Only when activated is it apparent. Like genes, we have all genes that we never hear about, and only when they are activated do they function. So what are the changes? First of all, synaptic efficacy can change momentarily, it can stay changed. Formation of new synapses, elimination of old synapses, and formation of connections, axons, and dendrites also is part of neuroplasticity. Programmed cell death, very important. Sometimes recognized as being something harmful or bad, but it's definitely extremely important. We'll come back to that a little later. The brain's function can change, as well as the spinal cord, as I mentioned. And we can get hyperactivity, hypoactivity, and so on and so forth. But important also is that information can be redirected. The flow of information can be redirected through the action of neuroplasticity. So what can activate neuroplasticity? As I said, neuroplasticity is not apparent until it's activated. And what is it that can activate neuroplasticity? Well, strange enough, lack of input to sensory systems is probably the most powerful activator of neuroplasticity. Stimulation of neurons at the same time, several neurons at the same time, can make these neurons form anatomical connections. That was what Herb mentioned, and neurons that fire together, wire together. In the parentheses, this statement so often cited in citation marks with Herb's citation. He never wrote that. It was an interpretation. It is a good interpretation, there's nothing wrong with that, but he never wrote that. But he wrote about a quarter of a page, which is summarized in this sentence. Other environmental factors, unknown factors, of course, lots of unknown factors can activate neuroplasticity. So let me first discuss the beneficial effect of neuroplasticity. That is what we know best, actually, and of course appreciate. So activation of other parts of the brain when some are destroyed by trauma or strokes is probably the most well-known effect and benefit from neuroplasticity. Changing demands prostheses, things like that, and if somebody use certain function, musicians use their specific fingers more than normal, will cause a change in the function of the central nervous system, but even the mapping of the cortex, for instance, will change in that way, can change in that way. Harm, plasticity disorders, as I mentioned, maybe the most important one here is central neuropathic pain, pain that is caused by something going wrong in the nervous system, in the brain, not by stimulation of nociceptors as what is normal pain. Tinnitus, ringing in the ears, have all kinds of forms, can be debilitating, and hyperactivity of motor functions, for instance, spasticity, but also spasm of various kinds. So there is no doubt that activation neuroplasticity can help recover from trauma, reroute information, and so on. But it requires that these functions have a redundancy so that it can be shifted, so that function can be shifted to another part. One example is speech. That is exclusively left side of the brain. So if you have a damage of the left side of the brain, it's very difficult to cure that kind of aphasia or to make the person speak then. Changing demand, cochlear brainstem and brainstem implants are examples of that. Cochlear implants and brainstem implants are used for deaf people and generate an electrical signal that stimulates auditory nerve or cochlear nucleus. The use of artificial limbs, of course, also requires reprogramming of the motor control. That is also a matter of neuroplasticity. Cochlear implants, let me just use a few minutes to describe what cochlear implants really are. They are, as I said, devices that generate electric signals that from speech or from sounds that will then stimulate the auditory nerve electrically. So they bypass the selectivity, the frequency selectivity in the cochlea, They also bypass the neural transduction in hair cells, and they bypass other functions such as what we know as two-tone inhibition and the traveling time on the basal membrane. So that is really a very different kind of coding than what the normal cochlea provides. Here's just a diagram of a very simplified, an early cochlear implant. You have a speech processor. Was only speech that was interesting at that time because that was the best one could do, of course, and an encoder, and then you had to go over the skin. You cannot have permanent wire through the skin that will get infected and so on. So you have to have something that bypasses the skin, and here you have the implanted electrodes and in the auditory nerve. It is implanted in the cochlea for stimulating auditory nerve. More recently, more than one channel was added, so there were a number of channels, and the research from analysis, synthesis, telephony in the 1950s, developing the channel vocoder, is actually used now in modern cochlear implants. And what is that? That is a device that only provides spectral information. It separates spectrum in slices and provides information about the energy in these slices of the audible spectrum. And it discards fine temporal information. And that was, of course, strange that was possible to get speech discrimination just on the basis of the spectrum of sounds. It took some time until people really accepted that. Here's a diagram of a modern cochlear implant device, and has filters that slice up the spectrum, rectifiers, filters, and then some processors, and then generate impulses, electrical impulses that is applied to electrodes that are placed along the cochlear basal membrane, stimulating different groups of nerve fibers. Adding more channels was, of course, something that helped. The first cochlear implant had one channel only. They gave sound awareness, not really speech discrimination, but more channels helped. But the strange thing is that the number of channels needed, or the number of channels about which there is no more gain, is only 8. So we can understand speech with information in 8 frequency bands only. That is remarkable, because the cochlea does a much more fine analysis, of course, of speech, of sounds. But if you look at other systems, look at the trichromatic visual color vision, then it works exactly the same way. It only has three bands actually, and the energy in these 3 bands tells exactly what the color is, and the nuances of colors over the entire visual spectrum. And the same occurs, of course, then with sound, and that is why we can understand speech in these few channels. But it certainly does just need the brain to change. It needs to reprogram the brain in order to be able to understand speech. And it is a good example of redundancy in both the auditory nervous system and in the speech signal in itself. We can take away large parts and we still have speech discrimination. That is good. So the young person is, of course, more malleable. The brain of the young person is more malleable than the older one. So if we would look at some measures of the success of this change in the function of the brain, evoked potentials recorded from electrodes placed on the scalp can be of some help is a kind of potentials where there's one component we call P1, and the latency of that component, which is the latency of that component, decreases with age normally. Here is the range where it does. And if we have individuals with cochlear implants at 3 to 5 years age, then they can recover, so their latency of the P1 actually end up in the normal range. But if we wait to 3.5 to 6.5 years, then you will see that they really never really make it. If you take adults, then about 7 years old, then you will see here they really never make it. So there is a limit for what the brain can change, and that limits go down the older we are. So it's important to give children, young children, cochlear implants. In the United States, the Food and Drug Administration prohibited implantation of cochlear implants in young children for many years because of ignorance of the authorities. So let me turn to some other topic, namely what happens when things doesn't go so well. Maybe plasticity disorders, activation of neuroplasticity that can cause harm. I mentioned before pain, what we call central neuropathic pain. It is pain that is not caused by stimulation of nociceptors, as when somebody steps on your toe. Then this is a different kind of pain. It's maintained in the brain without any help from outside. Chronic tinnitus. Tinnitus, of course, have many forms. Most people have probably heard little sound, little beeps and things like that, don't pay any attention to it. But there is severe tinnitus that is totally debilitating, that will make people not being able to sleep, not being able to do intellectual work or function in general. Spasm, of course. Strange enough, there was, when you have a trauma to a nerve, for instance, in the face, a motor nerve, then what will often happen is that when that recover, when the nerve recover, grow up to have synkinesis, which means involuntary contraction of other muscles than those that are intended to be contracted. Synkinesis, people thought that this was because the nerve fibers didn't find their targets. Not true. It's a change in the basal motor nucleus through neuroplasticity, because it has been without function for a while. Then this is about neuroplasticity, and synkinesis can be alleviated by training. Spasticity, of course, which we have in spinal cord injuries, for instance, is also to a great extent a matter of neuroplasticity. So, what does neuroplasticity activate? When neuroplasticity is activated, then several structures are involved. We have an activation of the neuroplasticity here, and it may cause pathology, may cause changes in the function of some structures. These structures will then send a different message to the next structure. This structure may be normally functional, but it receives abnormal input, and it will also produce abnormal output because of its abnormal input, but there may not be anything wrong with that structure, and so on, and then eventually we'll come to a perception of this perception of the symptoms of this whatever it is that was caused by the neuroplasticity. So this has an importance, because if we try to cure this disease. And we focus on this, for instance, here. This structure generates abnormal activity, but there's nothing wrong with the structure. So if we try to cure that problem by targeting that structure here, we don't have any success, because although it generates abnormal activity, there's nothing wrong with it. The reason is that it receives input from another structure, so we have to identify that structure. It's very similar to other disorders. Look at diabetes type 2. Two causes of first combined metabolic syndrome and genetics together. We get obesity, insulin resistance, hyperglycemia, and diabetes neuropathy. Treating the hyperglycemia won't treat the disease, although this is such an apparent sign of the disease. Here's just pain. As I mentioned, you have pain, the kind you get when you cut yourself or somebody steps on your toe. Normal, very important that this give a pain sensation. But you also have pain sensation without that can happen. Without that happens, namely from something going wrong in the central nervous system at neuroplasticity. Here are the pathways, simplified pathways from normal pain stimulation. You have two parts of the thalamus, dorsal and ventral. Ventral is the normal sensory pathway. Dorsal has connection to all kinds of other structures, such as the limbic structure, the limbic system, which is the emotional brain, such as the supplementary motor part, which has to do with the motor part, for instance, prefrontal cortex, which is probably where your soul is located, I guess. So this is what it tells what kind of pain it is, association for disease and so on. This pathway tells you where the pain is. So I won't go into this complex diagram of pain, but you see there are many different kinds of pain. So if you say pain, you have to tell what kind of pain it is, because it can be many different things. I just mentioned that pain from viscera is perceived much different. It's referred to the surface of the body. You don't have pain in the spleen, but you have pain somewhere on the surface of the body, and so on and so forth. Here you then have pain that is not caused by nociceptor stimulation, but which one part is central neuropathic pain, but you have inflammatory pain, and you have pain stimulating nerves in other ways, compressing nerves, for instance, irritating nerves, and so on and so forth. So there are many ways that you can have pain, and here's just a diagram that shows you simply where that come from the dorsal horn of the spinal cord, spinothalamic tract, and then ventral and dorsal. This is where, this is how, so this tells you where it's located. This tells you what kind of pain it is, burning pain, emotional reactions, and so on and so forth. And this is coming out of two different parts of the thalamus. Misspelled, I see right now. This is what you always see, that your slides are misspelled. You don't see it when you look at them for the 20th time at home, but I see it when you show it to a public. So this is what is interesting from a neuroplasticity point of view, namely the neuropathic pain, of course. And it is here again the neuropathic pain pathway. We have pain sensation, we have emotional symptoms. Not only does it hurt, but it also, in depression, also other affective disorders can be related to this, what comes out of the dorsal medial thalamus in that way. And we have allodynia, a slight touch of the skin give a pain sensation. It's called allodynia, abnormal rerouting of information, obviously, that occurs. Tinnitus is, of course, sound perceived where there's no physical sound. And you can have exactly the same diagram here. You have some kind of a program that control these changes, and then you have dorsal and ventral thalamus, auditory cortex, perception of the tinnitus of sound, and then you have connections to the limbic system, emotional reactions of the sound. So rerouting and change of excitability. These two factors are typical for neuroplasticity. Just again to remind you about the diagrams of these, the dorsal medial thalamus also receive input from other sensory systems. This classical pathway only has one sensory modality. If it's hearing, then these neurons will only respond to sound. But the dorsal medial thalamus, which we call the non-classical pathway, the neurons will respond to other sensory input, visual, tactile, and so on and so forth. So here's just the routes to the emotional brain, exemplified here by the amygdala nuclei. We had the normal route coming ventral thalamus, and then up to the primary cortex, association cortices, to the lateral nucleus of the amygdala. But the non-classical pathway has a subcortical route to the amygdala, and this is maybe what caused these emotional reactions not amenable to reason. You have people who have severe tinnitus say that I'm afraid of sound, phonophobia, I'm afraid of sound. No, it's not a dangerous sound, but I can't help it. I'm afraid of it anyhow. And that is probably something that is communicated this way there. So there's also changes in other parts of the brain when one exposes animals to very loud sounds that would give tinnitus in individuals, in people. That's the way we usually study tinnitus. And then we will find that other systems of the brain, non-auditory systems, non-sensory systems are involved. In the hippocampus, there are place cells. This is for study of rats. We have a maze here, and these cells fire only when the rat is in one part of the maze. They are called place cells, and they will do that. This is just another rat in this other location. But after sound exposure, after exposure to very loud sounds, which we believe gave these animals tinnitus, you will see that the response is in all kinds of places. So the place cell arrangement has changed because of what we believe is tinnitus, definitely because of exposure to sound. Plasticity, as I said before, can be activated by deprivation of input. Deprivation of input, you cut the auditory nerve, for instance, that's a dramatic form of deprivation of input, and here's what will happen then. There will be immediate changes in our RNA and the cochlear nucleus. Synthesis will change, there's a feedback system and so on, and this will give abnormal activity and more central structures. And again, if you try to cure these structures here, there's nothing wrong with these structures here, they just receive abnormal input. So it's important to keep in mind that it's not only the structures that behave abnormally that are abnormal, but they are also structures that are totally normal, but they behave abnormally because they have abnormal input. Balance disorder is probably a prime example of neuroplasticity. It of course moves the eyes so that you keep an image steady on the retina, and you don't have any sensation of that. But if you have some diseases, or if you have had too much to drink the morning after, you will definitely feel that you move your hands. That means that the information from the balance organ in the inner ear has been rerouted to some conscious parts of the brain. Typical rerouting, opening of dormant synapses. They are disorders, of course, of vertigo, the world is spinning, that are also related to neuroplasticity. Spasm, involuntary muscle contraction associated with synkinesis, is also often a matter of, also caused by neuroplasticity. Hemifacial spasm, for instance, there's much discussions about what was caused by that, but we know now that two things needed: an irritation of the root of the facial nerve by a blood vessel, and some abnormal factors. They have to be there, both of them, and obviously cause a faulty program that changed the function of the facial motor nucleus so that spasm resolves. Here's the treatment of hemifacial spasm, is treating that, because that is easy to treat and it is needed. We have no idea what this unknown factor is, and so on. So activation of neuroplasticity can make information reach other parts of the brain and the CNS, I mean also the spinal cord, that normally does not receive such information. And this may occur by unmasking of dormant synapses or by creating of new connections. So it can explain, of course, why plasticity disorders can be associated with so many different kind of symptoms. Development, as I said in the beginning, the blueprint is made by genetics, or epigenetics, and of course environmental factors of various kinds, and some unknown factors, of course. And the activation of neuroplasticity is absolutely essential in early life in order to obtain, in order to get a normal functioning central nervous system. And the plastic changes that are initiated normally in most people without any action, just programmed, is changing what the epigenetics program has laid out, and causing that by pruning, cutting connections, eliminating synapses, and so on, programming cell death, and that will then result in normal development. So the adult has much fewer cells, much fewer synapses than the young individual. Sometimes we think that it's the other way around, but this is not so. So apoptosis, synapse, adjustment of synaptic efficacy are absolutely necessary for normal development. So this mid-course correction after the genetically controlled or Darwinian development of the nervous system, if that does not proceed normally, we get developmental disorders. One example is autism, or actually autism spectrum disorders, because autism is a name for a large group of disorders. And the signs, the symptoms of autism is, of course, problems with social interaction, abnormal perception of sensory input, and emotional problems that can be thought of as problems related to the emotional brain, to the amygdala. So we can speculate that insufficient pruning of programmed cell deaths are involved. And it is known that the amygdala and other brain structures in autistic children have a higher packing density than normal. Actually, autistic children have a slightly larger brain in average than normal also. So, what is it that happens? We have genetics and environmental factors and a program, again, that should control these, I mentioned, pruning, programmed cell deaths, and so on and so forth. And if that does not proceed correctly, then we get developmental disorders. As I also mentioned, when we treat plasticity disorders, we have to be aware that there are parts of the brain that function abnormally, not because that part is pathologic, but because it receives pathologic input. And it doesn't help much to treat that. Also, plasticity can create bistable neural circuits, which means that they will flick into their abnormal mode. Central neuropathic pain is sort of it as being caused by bistable systems in the dorsal horn of the spinal cord that flip over to a pathologic functioning, and then you of course have to flick them back. They will not flip back by themselves. That's what is said by a bistable system. It's stable in both the normal and the pathologic condition. So just to repeat what I've said before, that you have activation of plasticity and some pathology somewhere, and that sends abnormal activity to other structures that may be totally normal in functioning, but will generate abnormal activity because they receive abnormal activity, and that will eventually give perception of whatever that is, pain, tinnitus, or something like that. So to cure these disorders, we should attack the programs, or those that are pathologic, not those that behave as they were pathological. So, in summary, the brain is plastic, for good or for bad, beneficial or harmful. Expression of neuroplasticity provides a mid-course correction of genetic programs, and we have a possibility of adapting to changing domains, rerouting information to functional parts of the CNS in stroke patients, for instance, and so on. These are the good part of neuroplasticity. And that is the part of neuroplasticity that is by far best known. Much less is known about the bad part of neuroplasticity, which cause tinnitus, central neuropathic pain, and can cause systems to operate stable in different modes, in abnormal modes. So I was asked to speculate about what is life. And I must say that it depends on the observer. Like most other things in life, it depends on the observer. And you all know the story about the 6 blind men and an elephant. And they get totally different view of what this structure is, the elephant. But one thing can at least be said, I think, safely, and I think most people would agree, that life is dynamic, and that is both for good and for bad. And also, life provides opportunities which of course is something that we all should take into account. So, with that, I'd like to thank you for your attention. Thank you.
Thank you very much. Very talk. So we now discussion, question, comment.
So a lot of the plasticity you spoke of involves physical changes. I wonder if chemical changes in the absence of physical changes would also be considered plasticity by your definition.
Absolutely. Chemical changes, for instance, changes in synaptic efficacy. You can think of that as chemical change, but of course also change in neural transmitters is of course a powerful inducer of changes that I would call neuroplasticity, yes. Okay. And they can of course, again, be for good or for bad.
Just to follow up, I was interested in your comment early on that lack of sensory input is a powerful inducer of certain plasticity changes. We probably all know people who meditate, some shorter periods of time, some for hours. I wonder if they know something that we don't, that their meditative practice, which in fact is lowering the sensory input, might be changing their brains in some way.
I think they will. I think they will change. I don't know what a few hours will happen, but definitely it will definitely change. But it has some very practical implications in treatment of various disorders. You will have a patient with an intractable pain in her hand, for instance, and she say, I would much rather be numb. Or you will even have people who have intractable tinnitus in one ear, and they say, I would much rather be deaf. Could you cut my auditory nerve? And this is an absolutely no-no, because that will just cause problems worse. And you have tinnitus in patients who have separate auditory nerve, of course.
Thanks for an excellent and wonderful lecture. The only question, where have the stem cells come into your world? Have they altered anything in your picture?
They are in the newspapers.
You read the newspapers?
They are in the newspapers.
Yeah, they are, but they're also in the brain.
Well, they're probably everywhere, but I don't know if they have any. They're very popular now. I mean, this is the popular thing. We're going to treat everything with stem cells, and people try to treat spinal cord disorders. I mean, trauma to the spinal cord with stem cells, and I mean, I know that old people get pessimistic, but I must say, if you just glance into the complexity of the spinal cord processor, then I have very difficult to understand how just outgrow of new cells should be beneficial. I mean, this is not what the problem is, but it's very popular right now.
I would say it's also real. We do it in Lund, and we can see that they really colonialize the area of the brain where there is a stroke, shown in animals so far. And also tumors, we can direct things to the tumors by the stem cells.
Well, that's
in animal reality.
That's a different thing. Tumors are different things.
Oh yeah, I agree.
I mean, trauma.
You still see those small friends working hard in the brain, those stem cells that are there. So maybe might add something in the future. Thank you very much.
In partial answer to Professor Diemer's question, Richard Davidson at the University of Wisconsin has studied has studied the brains of long-term meditators, Buddhist monks. And I think I remember one of his results, and it goes like this, that if you have heightened activity in your left prefrontal cortex, you feel better. If you have heightened activity in your right prefrontal cortex, you feel worse. And these meditators had heightened activity on the left side.
Sounds reasonable. It sounds reasonable. That's very good. The lack of input, sensory input, is important in tinnitus, for instance, because many patients with many individuals with severe tinnitus, they are bothered by sound, so they try to avoid sounds, which actually makes things worse. So one treatment is to ease them into listening to sound gently, and that will help. But also, if you take individuals, say individuals over 50 years old or maybe over 60 years old, put them in an absolutely silent room, most of them will have tinnitus after a short time. But whether this is neuroplasticity, it probably is, because there's another thing people thought earlier, that neuroplasticity took a long time to act. But many of these, for instance, the RNA that I mentioned, is almost instantaneous.
How is it difficult to switch the two modes between good and bad? Because it is very useful in the cureness.
Yes.
Because on the one hand, it is the onset of disease. On the other hand, it is the possibility of cure of such emergent disease. How is it difficult to see?
Well, it is, I mean, you have the problem that by trying to cure, for instance, pain, earlier days people would, as I said, maybe even cut nerves. Now they will block nerves, which I don't think is a good idea either. And that is, of course, a way of introducing bad plasticity in an attempt to cure something. That can happen. The interesting and far more complex thing is, of course, the developmental kind of things. And it turns out that if you have autism, we know very little about autism, of course, but there are various attempts to treat it, and some attempts consist of training of some sort. Speech therapy, for instance, is very popular. And it turns out that if you compare individuals who have had that kind of training and other individuals with no training, the speech therapy people, they do much better. So it improves also other functions. We don't know how this works and so on. Stimulation, I mean, I said absence of stimulation is bad. Stimulation is used for treating pain. You have what's called TENS, transderm electric nerve stimulation. Electrical stimulation of peripheral nerves is an effective way of treating severe pain. So that is the other side. Instead of eliminating input, you create new input, and that can be very, very helpful.
Thank you. I have a question about neuroprosthesis. So you mentioned about the neuroprosthesis for hearing. So it seems to be quite successful. Also, there is some critical period. But I hear that the neuroprosthesis for vision has not been successful so much. So I'd like to know the possible difference between two, the vision and the hearing. So what's the difference?
Yeah.
So what's the cause?
It is absolutely correct. In fact, people try to do visual prosthesis long before they try to do auditory prosthesis. So the problem is not lack of time. But there have been many different attempts. Mainly, the attempts have mainly been to place an array of electrodes on the surface of the visual cortex, and then send electrical impulses to that array. And it has not had much effect. It has not had much benefit, I would say. Actually, very little benefit. And I don't know why. I don't think that they will have success in placing electrodes on the auditory cortex for hearing, because when it comes to the auditory cortex, it's so much processed, so we have no idea how the code really is in the auditory cortex, and it's probably similar for the visual cortex.
is there any possibility to recover, for instance, the cocktail party effects? Okay, so in the cocktail party, so you can hear the other person's voice.
With cochlear implants.
Yeah, so, right.
It's remarkably well now. There are many of these people with cochlear implants who can use the telephone, for instance, and who do very well in an environment of other speakers. Yes, it is remarkable. It is remarkable how well these prostheses really works. I could say something about brainstem, what is called brainstem implants, are implants on the cochlear nucleus for people who have what lost their auditory nerve, for instance, in neuroplasticity 2, where they have repeated tumors on the auditory vestibular nerve, and the auditory nerve is severed, so it doesn't, of course, doesn't help you to have cochlear implants, but brainstem implants on the cochlear nucleus, were used only for these patients who had such operations. And the results were terrible. They could recognize sounds, but never speech, never discriminate speech. But recently, among other, a surgeon I worked with in Verona, Italy, Vittorio Coletti, started to do that in patients who had two kinds of patients. Patients who had the auditory nerve severed in accidents, and children who had a constricted or not opened internal auditory meatus, so the auditory nerve was strangled. And by using cochlear nucleus implants in these individuals, he got enormous results, almost as good, actually as good as you get in cochlear implants. So there's something strange with neurofibromatosis too that also affect the cochlear nucleus, probably, or something like that. But it takes somebody to have the courage to do these kind of things, because you would say, well, you shouldn't use cochlear nucleus implants because we know that they don't work very well in people with no auditory nerve for other reasons, for instance. But he had the courage to do that and got tremendous results.
Yes.
Just on a practical matter, I had tinnitus when it started about 30 years ago, and it was quite severe. But then I was experimenting with my ear and it oscillated over a long number of years. And the tinnitus has almost gone away. There's just a slight suggestion of it there today, but this might give some indication of how we deal with the mind.
Could very well be. Tinnitus is a mystery in many ways. It's very difficult to understand why it goes away in some certain circumstances, and definitely also is difficult to understand why it's there at all.
I have tinnitus too, but my question is about something else. You mentioned transcutaneous electrical stimulation for the treatment of pain, and I feel compelled to mention that it doesn't work nearly as well as the originators of the gate control theory, Melzack and Wall, anticipated that it would. And secondly, that it's a very special case in which stimulation of one kind of nerve is thought to dampen activity, and the second kind of nerve, which is the kind of nerve that carries pain, the C fibers. And so in that sense, it's not a very generalizable example.
It's true. There's really no generalized treatment of these disorders, which of course indicate that they are not one disorder, but many different disorders. But you're absolutely right. The Melzack-Wall gate hypothesis is probably a little bit put on the side right now. But there's essentially two ways that that transderm electric stimulation can work, and that is directly on the spinal cord because it activates large fibers that have inhibitory influence on those that transmit pain. But the other way is a little more long-term, and that is by its effect on the brain as inducement of neuroplasticity, or reversing neuroplasticity probably. But the problem with this kind of treatment is that you have to do it correctly. You have to have the right frequency, you have to have the right stimulus strengths, and so on. And it's very difficult to get patients to do that. It's much easier to get them to pop a pill twice a day or 3 times a day or something like that. And that is one of the problems with treatments like TENS, that it requires cooperation with the patient.
So you write down in the synopsis how to measure the plasticity. And so you write down the functional imaging is hopeful. But
well,
for instance, the functional MRI is still weak for the time resolution, and other imaging is still weak for space resolution.
Well, it has of course been used, the functional, so-called functional MRI has been used, and somebody believes in it and somebody don't. And I probably belong to one of those who don't. Here is a picture that shows this potentials that I mentioned, this P1 that I mentioned, and how it's distributed normally in on the brain. And what happens in early implanted children. I don't know if you can see a much similarity with the normal one. This is the normal one, and this is the early implanted, which are doing very well. And here's a late implanted, and somebody say that they can see some systematic changes. I can see some changes, but I'm not really sure that I can see any systematic changes in them. And it is very difficult to interpret these so-called functional MRIs. And when you try to do something else like magnetoencephalography, then you've got a poor coincidence with these studies. So I think they need a little more years on the back.
Perfect. If you don't have any question, so thank you very much again.